Assalamualaikum warahmatullahi wabarakatuh. Good morning. Today I will continue the electronic circuits one. After we discuss about the introduction in first week, so in second week we will discuss about the semiconductor diodes. There are many subchapters here. The first one is semiconductor material and covalent bonding and intrinsic materials, and then energy level, extrinsic materials, semiconductor diodes, ideal versus practical, resistance level, diode equivalent circuits, capacitance, reverse recovery time, diode specification sheets, and also Zener diodes, and also the last is light emitting diodes. Okay, this is the semiconductor diodes. The first one, this is some material that we can use to design a semiconductor or diodes. There are germanium, silicon, and gallium arsenide. And I think you have learned it in semiconductor devices course before. So, semiconductor comparing with the conductor and insulator, semiconductor are special class of elements that the conductivity is between the conductor and insulator. And mostly the material to design a semiconductor is germanium, silicon, and gallium arsenide. And you can see the germanium and silicon is material in column 4, or they have 4 electron valence. So, and also the gallium arsenide is combination of the column 3 and also column 5. So it also have a 4 electron valence. So this is the comparison between the germanium and silicon and also the gallium arsenide. The germanium has a conductivity higher than silicon and also gallium arsenide. But the resistivity of the gallium arsenide is the largest one comparing to the germanium and silicon. But you can see that the gallium arsenide has a larger area between the resistivity, the resistivity of the gallium arsenide. It means that if we do some special doping in gallium arsenide, we can choose whatever gallium arsenide will lies in resistivity and conductivity. I mean that if we put a small doping, maybe the conductivity will be like over there. But if we increase the doping, the conductivity of gallium arsenide will higher like in these ones. But you can see that the germanium and silicon, the range for conductivity is lower than the gallium arsenide. So this is the insulator here and semiconductor and also conductor here. So this is some application using the materials. I will skip this one, but you can see that for the lower frequencies, like from 0.8 hertz to 5 gigahertz, mostly we use the silicon here. But if we change the frequency higher than 5 gigahertz, we using the silicon germanium and also gallium nitride. And if we use the frequency much more higher, like 94 gigahertz for imaging, so we jump to another material like gallium arsenide, MEHMT, or indium phosphate here, HBT. Okay, so every material has a characteristic to design specific frequency. So for silicon, it's very common used in low frequency. And this is the covalent and intrinsic material. So we can see that for silicon, silicon has four valence band here, 4 electron in valence band, and germanium also has 4 electron in valence band like there. And we can see that the gallium, column 3, it has 3 electron valence, and arsen has 5 electron valence here. Okay, so the atom that have 4 valence electrons called tetravalent, and 3 is trivalent, and 5 is pentavalent. So to become the octet, the electron must be shared between one material to another material. So in valence band, we have 8 electron valence. Okay, so it's like this one. We have the silicon. Silicon has 4 electron valence, so they bond with another material like silicon here. Another silicon has 4 electron valence. So total we have 8 electron valence if the silicon has the covalent bonding like this one. And the silicon share the electron between another silicon like this one. So this is the sharing electron of this silicon and also this silicon. Okay, so the sharing of electron, we call it covalent bonding. Okay, and what happened in gallium arsenide crystal? Gallium arsenide has 3 electron valence, this one, 2, and 3. And arsen has 5 electron valence, 1, 2, 3, 4, 5. So to become octet, they must be have a covalent bonding. So 3 plus 3 plus 5 is become 8. So 8 is octet. So we can use the gallium arsenide as another semiconductor. It's like a silicon and also germanium that has 4 electron valence, and they have a covalent bonding with another silicon or another germanium. Okay, so this is the intrinsic carrier. Every semiconductor has the intrinsic carrier. Intrinsic carrier is mean that the amount of carrier per cubic centimeter is like gallium arsenide. We have 1.7 cross 10.6, and then silicon and also the germanium. Okay, the term of intrinsic. So intrinsic is mean that this is the pure semiconductor. We didn't dope. We didn't dope that this semiconductor with another material. So this is the intrinsic. So the impurity is very low. So it's like the essential pure can be made through the modern technology. Okay, so we can see that from this table, the germanium has the highest number of the intrinsic carrier, and gallium arsenide has the lowest intrinsic carrier. And this is the relative mobility factor. We can see that the gallium arsenide has the higher mobility than the highest mobility, and the silicon has the lowest mobility. So we can see from here, the germanium has the gallium arsenide has the carrier 1.7 multiplied by 10.6 intrinsic carrier. So the mobility in that semiconductor is highest. So it means that the intrinsic carrier, I write like intrinsic carrier IC, is lowest. So the mobility is highest. And we can see that the germanium has the highest intrinsic carrier. Okay. Okay, the germanium has the highest intrinsic carrier. So the mobility is not higher than gallium arsenide and also the silicon. Okay, so this is another, so the intrinsic carrier is similar to the mobility. If the intrinsic carrier is higher, it means that the mobility will be decreased, because there is no space in the semiconductor. So it's like in the road, if we have many cars in the road, So it means that the car cannot move freely. But if the car only a few car in the road, so each car can move free, and yeah, the speed is higher than if the car is if we have a many car. So it's similar to the semiconductor, the intrinsic carrier. Okay, so what is the energy level of semiconductor? So we can see that, and it's I think this is you have a discussion of this matter in semiconductor devices. In insulator, the energy gap between the valence band and the conduction band is very high, is more than 5 electron volts. But for conductor, there is overlap between the valence band and conduction band. So the electron in valence band can move easy to conduction band and yeah, free to move in conduction band. But for insulator, the energy gap between the valence band and conduction band is very high. So it's very difficult to move from the electron in valence band to conduction band, or the electron needs a very high energy level to move from the valence band to conduction band. So it means that the insulator, we cannot see that insulator it cannot and the current cannot flow in insulator. Yeah, the current can flow in insulator, but if we have the very high energy level, so we can see from this one, actually the electron from valence band can reach the conduction level if the energy coming from the outside of the insulator is very high. So electron can move from insulator to conduction band. Okay, so the term of the insulator is difficult to, yeah, the current is difficult to move in insulator is better than the current cannot flow in insulator. So difficult term is more, yeah, more appropriate to to explain the insulator characteristic than the then it's like a can move. So in this is a semiconductor, and in semiconductor, the energy gap is between the conduction band and the insulator. So we can see that every semiconductor has different energy gap. It's like germanium is 0.67 electron volt, silicon 1.1 electron volt, and gallium arsenide is 1.43 electron volts. It means that the gallium arsenide needs more energy to move the electron from the valence band to conduction band, and germanium needs the lower energy than the silicon and gallium arsenide to move to electron can move from the valence band to conduction band. So this is the energy level. Okay, so this is the energy level. This is the valence electrons. Okay, so every valence looks like this one, so it have the energy gap like this one. Okay. Okay, and the difference in energy gap require refill sensitivity is a type of semiconductor to change in temperature. So it means that from germanium has the lowest energy gap. It means that if the temperature increase, it's like in electronics board, if we plug in or switch on the circuits, the temperature will increase. So if we use the germanium as semiconductors, like for diode or for bipolar junction transistor or of FET, so the electron can move from valence band to conduction band and start to move in conduction band if the temperature is increased. Okay, because the energy gap is quite small. But from gallium arsenide, the energy gap is is higher. So if the temperature increase, maybe the energy the energy from the temperature is not enough for electron to move from the valence band to conduction band. Okay, so it's like from germanium, so we can use the germanium. It's like photo detector because it's sensitive to the light. So if the light is coming to the semiconductor, so the electron can move freely from the valence band to conduction band. But for transistor, like transistor or BJT, bipolar junction transistor, or FET, the stability is high priority. So the sensitivity to temperature light can be detrimental factor. So we try to use semiconductor with the energy gap higher. It's like silicon or gallium arsenide. So you can see, and in this application, yeah, there is no germanium. Yeah, just silicon here. And germanium, if we combine silicon and germanium, we can create the HBT or BiCMOS. So we can use the germanium. Why germanium? We didn't use the germanium for transistor because the sensitivity is very high. Okay, so after intrinsic material, we jump to the extrinsic material, N-type and P-type material. So N-type material, it's like, this is the silicon. Silicon is intrinsic semiconductor. And we put a stibbium in silicon. Stibbium, or antimony, is the 5 valence electron of antimony. So stibbium has 1 free electron if they have the covalent bonding with the silicon. And so this is the N-type material. N-type material is mean that the majority carrier is electron, and the minority carrier is hole. Okay, and for P-type material, we put the boron in the intrinsic material of silicon. So boron only has 3 electron valence here. So once bonding with silicon is void, so we can see that this is like a positive or a hole. So the majority carrier of P-type is positive, and minority carrier is electron. Okay, so if we dope the arsens, boron, and phosphor in silicon, so we can see that if we dope the silicon with the arsens, it means that arsen and phosphor, this is the column 5, and boron is column 3. So we can see this is the N-type. So this is the N-type, and this is the P-type. So N-type material has the higher mobility. So the N-type has higher mobility than P-type in mobility. Okay. Okay, so this is how to calculate the mobility in silicon. So the first one, the parameter, we have 4 parameter: mobility minimum, mobility maximum, and reference, and also alpha. We can see this parameter in datasheets of the material. So we can use mu minimum is from datasheet, mu maximum from datasheet, mu minimum also from datasheet, and alpha is from datasheets and reference. So in this calculation, we only can make a variation of the n. N is number of doping. So if we increase the n here, so the mobility will change. Okay, and this is the electron to hole flow. So the electron flow is like this. this one to the right side and hole to the left side. Okay, so this is the electron flow, electron versus the hole flow in the material. So n-type has the majority carrier of electrons here, and minority carrier is hole. And p-type has majority carrier of hole and minority carrier of electron here. Okay, I think this is the first part of the chapter 1. It's about the semiconductor. Before we discuss more detail in semiconductor diodes. Okay, thank you for your attention. Good morning. Assalamualaikum warahmatullahi wabarakatuh.